Okay, so today we're going to start a new chapter on sequences and series. So we'll do this for a few weeks. Then we've got Taylor series, and then complex numbers, and then we're done for the year. Okay, so I'm hoping to finish everything by early October. So that gives you plenty of time for the final exam. Okay, remember, final exam is 50% of your class mark. So if you mess up in the final exam, that's it for the whole year. Okay, so firstly, sequences. So we'll do that this week. And then the series, we will continue with that next week. Okay, so what is a sequence? So a sequence is a function. Okay, let's say A from the natural numbers to the real numbers. Okay, so for every natural number, we assign some real number. That is going to be our sequence. And here we're going to take the natural numbers to start from 1. Okay, so we're going to have issues with dividing by 0 if we start by 0. So we'll take this starting from 1. Okay, so we'll take that from 1 there. Okay, so the elements of a sequence are given by a subscript n. So usually when we have functions, we have like f of x. But in particular for sequences, instead of saying a of n, like a function, we just put that in the subscript. So we have a sub n, that is the sequence element. Okay, and then a little bit of notation. So usually we write out sequences like this. So we have a1, a2, a3, dot, dot, dot. Okay, with the round brackets to show the sequence. We could also write it as a sub n, like that. Okay, so like a sub n could be n squared over 2, for example. Then we would write n squared over 2, and then the brackets for that. Okay, and sometimes you'll see it with the curly brackets instead of the round brackets. Okay, so it depends where you look. It all means the same thing. Okay, some terminology now. So definition. A sequence an, so let's use this notation, is called convergent if we can take the limit as n goes to infinity of our an, and we get some number L that is less than infinity. So some finite limit. Okay. So if we get some finite limit as n goes to infinity, we say that the limit converges. Otherwise, we say it diverges. So either it converges or it diverges. It's one of the two. Let's have a look at some examples of these. Okay, so firstly, let's say we have an equals e to the minus n. So when n goes to infinity, the sequence will go to 0. That's a finite number, so this is convergent. Yeah, so that is a convergent sequence. An equals n squared. So here when n goes to infinity, the whole thing goes to infinity, so it is divergent. Yeah. And here we have an equals minus 1 to the n. So this one, we can't take the limit, because as we increase n, it just goes plus 1, minus 1, plus 1, minus 1. There's no limit to this. Since there's no limit, it's not convergent. If it's not convergent, it's divergent. Okay, so put a little warning there. The sequence may not go to infinity, but it could still be divergent. Okay, so here, if we look back up, we need this limit to be some L. Remember from last year when we did limits, this limit does not exist, right? Because it goes +1, -1. The limit doesn't exist. There's no limit value. It cannot be convergent, therefore divergent. Okay, so again, it is either convergent or divergent. There's nothing in between. Right. Any questions on convergent, divergent? Yeah? Yes. Divergent means not convergent. There's no in between. Either the limit exists, and so we say it's convergent, or it doesn't, and it's automatically divergent. Divergent doesn't always mean go to infinity. Okay. So divergence. Divergence is the same thing as saying not convergence. Okay, so alternating sequences are also divergent. Okay, from this definition. Right. Any other questions? Okay. We got a theorem. So this chapter and the next chapter will have a lot of theorem proofs. Okay, please prepare yourselves for that. Okay, theorem. If the limit as n goes to infinity of the absolute value of an is equal to 0, then the limit as n goes to infinity of an by itself is 0. So limit of the absolute value of the sequence, if that is 0, then the original sequence there is also 0. Okay, proof. Okay, like I said, there's a lot of proofs. Please expect something like this for the test and the quizzes. Okay, so we can use the squeeze theorem for this. There might be other ways that you can think of. This is just one way, right? If you think of other ways, that's perfectly fine. So we can use the squeeze theorem. Okay, so what can we do here? Well, we've got this absolute value of an. We know how the absolute function works from last year. So we can write this as minus the absolute of an is less than or equal to an, which is less than or equal to the absolute value of an. Right, we did that last year with the absolute values. Okay, so we've got an on the left-hand side with the minus, but don't worry about that. And we've got an on the right-hand side, okay, with the absolute values. And what we want is the limit of the absolute value to be 0. Okay, so let's take the limit for all three and see what happens to the left side and the right side. So we're going to take the limits for all three. So limits of the left one, limits of the middle, and limits of the right. Okay, so this sets up our squeeze theorem. We've got left, right, and middle. If the left and the right match, then the middle one also has that limit. Okay, so let's look at the left and the right. So we'll call it 1 and 2. So for number 1, we've got the limit as n goes to infinity of minus the absolute value of an. That minus 1 over there, we can take that out of the limit. So it's going to be minus the limit as n goes to infinity, absolute value of an. Now, what do we know about that limit? Okay, we'll go back up here. If this, then that, what do we know about the limits with the absolute value? It's 0. Good. So this is 0. So we know the left side limit is 0. What about the right side limit? Let's have a look. So here, this one's a bit easier. So we have the limit n goes to infinity, absolute an. What do we know about this one? Also 0. So we've got the left limit is 0, the right limit is 0. So the squeeze theorem says that the middle one is also 0. The squeeze theorem says the middle limit is also 0. Yeah, so we can write this as the limit n goes to infinity of that middle one. The a sub n just by itself there is also 0. Okay, quick show of hands. Who forgot the squeeze theorem from last year? Okay, not too many, so I won't go through that again. What's this noise? I'm asking. If you forgot it, I'll go through it. No one put up. One person put up their hand. See me afterwards. We can move on. Right. Any questions about the proof? Besides the one person, they'll see me after. Okay. Let's have a look at the next one. Okay, so a theorem. If the limit as n goes to infinity of a sub n is L, so we already know that this is convergent. It's got a finite limit, so it must be convergent. And f is continuous. Okay, we know what that means from last year. What does continuity mean? Yeah. I mean, yeah. In terms of limits, what does it mean? So at a point, what do we do about the left and the right? Yeah. In terms of limits, what do we say? Yeah. Yeah. Left limit, right limit must match up. Good. Okay, so if f is continuous, we know that limit x goes to a. So I'll just put the little definition at the bottom here. So x goes to a minus f of x equals limit x goes to a plus f of x equals limit x goes to a f of x equals f of a. So this first part in pink, that's for the limit to exist. So the left and the right limits exist. That means the limits exist. And then this blue part, that means it's continuous. So blue part is continuity. The pink part is the limits exist. Okay, and continuity, you see it mixes the two there. Okay, so we've got the limits of the sequence exist, so it's convergent. And we know that f is continuous, which means we know that the limits can jump inside the function. So the limit as x goes to a is just f of a. Okay, so with that, let's have a look at the proof. The proof is obvious. Okay, we just need to rewrite the limit. That's exactly the proof. So we've got the limits. Then we got f of L. So here we just take the limits inside there. So we got the limits n goes to infinity, f of a n. But we know f is continuous, so the limit can just jump inside. So this will be f limit n goes to infinity a sub n. Okay, since f is continuous, limit jumps inside there. Okay, but since the limit's inside now, the limit as n goes to infinity of a n, that's just L, so we get f of L. So you write one line there just to show that the limit jumps inside because f is continuous. So limit goes inside since f is continuous. So just one line using the definition of continuity. Okay, quick example just to show how we can use this. So let's say we have the limit n goes to infinity of sine of pi over n. Okay, we know sine is continuous. So instead of looking at this outside, we can just put the limit inside and have a look at the inside part. So this is going to be sine of the limit as n goes to infinity, pi over n. Right? We can ignore the sign, the limit can just jump ahead inside. Now the limit as n goes to infinity of pi over n, that's just 0. We know that from last year. So we get sine of 0, that's just 0. Yeah. So, right, just a recap of what we did last year. Okay, now for the new stuff. So we're going to be looking at the monotone convergence theorem with the proof and the applications. Okay, so that's the new stuff for this year. The monotone convergence theorem. Proof and applications. Yeah. So that's the main thing for this chapter, is this theorem, the proof and applications of it. Okay, there's a little bit of side stuff we have to do first. It's just terminology, and then we'll get into the theorem. So definitions. Okay, so this is just terminology for the different things. So a sequence AN is called increasing if AN plus 1 is bigger than AN. So in other words, the next term is larger than the previous term. For all n. Okay, so that's what we mean by increasing. The next term is larger than the previous term. A sequence A sub n is called strictly increasing if A sub n is strictly less than A sub n plus 1 for all n. Okay, so increasing, that has the possibility of them being equal. Strictly increasing, they can never be equal. Okay, and then we have the same thing for decreasing. So a sequence A sub n is called decreasing if A n plus 1 is now smaller than A n. Okay, so the next term is smaller than the previous term, then it must be decreasing. Okay, and you can guess the next one, strictly decreasing. That's going to be a sequence. A sequence A sub n is called strictly decreasing, sorry. Okay, you can guess what that's going to be. The next term must be strictly smaller. Okay, for all n. Okay, so very simple definitions for increasing, strictly increasing, decreasing, strictly decreasing. Any questions for these four? Okay. Let's have a look at some examples. Now, showing if the sequence is increasing or decreasing, there's quite a few methods. We'll go through one of each, and then you can pick whatever one suits you best. Okay, so example number 1. Show that a sub n is equal to 3 over n plus 5 is decreasing. So for this example, we'll use the first method, and then I'll show you one of each for the other ones. Okay, so what we do is we look at the next term, and we try and show that it is smaller than the previous one. So let's have a look at what the next term is going to be. That's going to be a n plus 1. Okay. So in place of n, I'll put n plus 1. So that will be 3 over n plus 1 plus 5. Okay. So I've just had a look at the next one. Now we're going to do a little bit of rearranging in this denominator. I'm going to write it as 3 over n plus 5 plus 1. Okay. Just a bit of rearranging with the brackets there. Now 3 over n plus 5, that's what we have for the previous term. But here we've got an extra plus 1. Okay, so here we've got this extra plus 1 in the denominator. If we ignore this plus 1, then the fraction gets larger or smaller if I get rid of that plus 1. So we've got this thing here. We get rid of the plus 1. Did I make it larger or smaller? Larger. Good. Okay, so taking away the plus 1, I make the fraction larger, which means this is going to be smaller than if we get rid of the plus 1. Okay, so we take away the plus 1, it now becomes larger. But this 3 over n plus 5, that's what we started with the an. Okay, so what have we shown? Let's look at the left and the right. We started with an plus 1 over there. We know that an plus 1 is now less than or equal to, and then right on the other end, an. So we have shown an plus 1 is less than or equal to an. When we go back up a little bit, if an plus 1 is less than or equal to an, it must be decreasing. Yeah, which is what we wanted to show. Any questions about this first method? No questions. Okay, let's have a look at the second method with another example. So example 2. Show that a n equals n over n squared plus 1 is decreasing. So what we're going to do is first assume that it's decreasing. We're going to write out that formula. Then we're going to have a bunch of algebra steps all the way down. And we're going to show that what we started with was true. So we're going to assume that an plus 1 is less than or equal to an. Okay, we're going to start assuming that it's decreasing. Then we're going to write out a lot of algebra steps, and we're going to end up showing that this statement is actually true, which is what we wanted to show. So this is equivalent. We write it like this with the double arrow. So this statement is equivalent to some other statement, and that's going to be just substituting the formula. So an plus 1, we just replace n with n plus 1. Okay, less than or equal to an. Okay, and these are exactly the same, right? That's what we mean by equivalent. So we have an plus 1 is less than or equal to an. All we did was substitute the formula, so these must be equivalent. We haven't changed anything. Okay, so let's look at this right-hand side. We're going to do a bunch of algebra to show that this left-hand side here was true. Okay, so what can we do? So on each line, it must be equivalent to what we had before. Let's get rid of these fractions by cross-multiplying. So we're going to have n plus 1. N squared plus 1 is less than or equal to n plus 1 squared plus 1. Okay, it's a bit easier working like this than working with the fractions. Okay, but we can just distribute. That doesn't change anything. So this is equivalent to the same thing, but if we distribute. So that's going to be n cubed plus n squared plus 1. We haven't changed anything, we've just distributed. So this is less than or equal to n. N plus 1 squared, that will be n squared plus 2n plus 1, and then we've got another plus 1, so plus 2. Again, we haven't done anything, we've just simplified. Nothing's been changed. Okay, so this is equivalent to, we can distribute the n inside, and that doesn't change anything. So that will be n cubed plus n squared plus 1, less than or equal to, distributing the n, that will be n cubed plus 2n squared plus 2n. Again, nothing's been changed, we've just done distributing. We've got n cubed on both sides, that can cancel. And then we've got 2n squared on the one side, n squared on the other side, we can cancel one of those. 2n on the one side, n on the other, we can cancel those. So we end up with 1 is less than or equal to n squared plus n. And we know that n is always greater than or equal to 1. Right, because the natural numbers, that starts from 1. Okay, what can we say about this statement at the end? If n starts at 1 and is always increasing, what can we say about that statement? So? Yeah. Yeah. That statement's always true. You can put any n value inside, that statement is always true. Right? For any n, you can plug in whatever you like. Statement's always valid. The statement's always true. Now let's look at the left and the right. So we've got this statement. an plus 1 is less than or equal to an is equivalent to, and we go all the way down, well, it's always true. Okay. And since it's always true, we know that this sequence is always decreasing. Because it's true for any n, so it's always decreasing. Okay, so an plus 1 is less than or equal to an for any n. For any n is always true. Okay, well, that's the definition for decreasing, so it must be decreasing. All right. Any questions? Yeah? Cross multiply. So this denominator on the left, I'll put to the numerator on the right. this denominator on the right, I'll put to this numerator on the left. Okay. You can try work with it as fractions, but that's a bit messy. Okay. Any other questions? All good. Okay. Last one. Example 3. So this will be the third method. Of course, there's many more. You can pick whatever you want. It's just 3 to have a look at. So example 3. Show that a sub n is equal to 1 over e to the n plus n is decreasing. Now, depending on what's given, it may be better to use method 1 or 2 or 3. But you can always use this third one. Okay, so what we do is we come up with a function f of x. So we've got the sequence. We're going to come up with the function f of x. So f of x is equal to 1 over e to the x plus x. Okay, so why does it look like this? Well, if I replace x with n, I get back my original sequence. Okay. So we come up with this function f of x, such that if we replace x with n, we get back to what we started with. But now the nice thing about f of x with the continuous variable x is we can do a derivative. So let's do a derivative here. Right, you can't do a derivative with the sequence because it's n. You can't do any calculus with that. But f of x, we certainly can. So this is going to be minus 1 over e to the x plus x squared times, and then the derivative of the bottom, that's e to the x plus 1. Now you can put in whatever x you like. This is always going to be negative. Okay. In other words, the gradient is always negative. So the gradient of f is always negative. Not sometimes negative, sometimes positive, always negative. That's very important. Okay. And if it's always negative, then f is decreasing. And if f is decreasing, then our sequence is also decreasing, right? Because we've got this special case here of f of n is an. So if f is decreasing, an is also decreasing. So this third method you can always use because you can take your sequence, you can write it as a function and do the derivative. Yeah. So this one always works. This one, if you try to use this method with example 3, that's a bit of a problem there. Example 1, it's even more of a problem, right? Because you have to try put in this inequality. So, depending on what's given, you can pick 1, 2, or 3, or something else that you find. Okay, but 3 always works. That should be your go-to. But again, with all the other stuff, if you want the bonus marks, do the other methods as well. Okay. But my recommendation, do 3, and then have a look at the other ones for bonus marks. So start with method 3. Okay. Right, that's just advice. You can follow it if you want. It's up to you. All right. Any questions? Yeah.
So for question using method 3, you already mentioned that the gradient of this is
Yes. So if you want to show that it's decreasing, then the gradient must be negative. If the question will show it's increasing, then the gradient must always be positive. Yeah, it's always the one or the other. All right. Any other questions? You're all good. Okay. Last bit of setup for the theorem. And then on Thursday, we'll go through the full proof. Okay, so definition. Okay, so we've got the definitions for increasing, decreasing. Now we've got the definitions for the sequence being bounded. Okay, then on Thursday, we'll combine it. Problem. Okay. So we've got the definitions for increasing, decreasing. We're going to go through the definitions for the sequence being bounded, and then the monotone convergence theorem will then combine the two. Okay, so please make sure you understand both parts. Okay, so what does it mean for a sequence to be bounded? You could probably guess a definition for it, but we have the following. A sequence AN is bounded above. Okay, so what do you think bounded above means? It means that as the sequence continues, it never goes past that bound. Okay, so we'll draw some nice pictures in a moment, but just imagine the sequence increasing, but there's some ceiling that it never goes past. So sequence AN is bounded above. If there is a number M, let's say a capital M for bounded above, such that a n is always smaller than this capital M. Okay. So M we call an upper bound of the sequence. So let's have a look at a little picture for this. So let's say we've got our sequence. It might do something like this. Okay, we see that we can define this number capital M there. And with the sequence like leveling off like that, we see it never goes beyond M. There's that upper bound. So we say it is bounded above. Okay, it could do something else. Maybe your sequence does something like this. Okay, so we've got the example with the white dots. It never goes beyond the pink line. And the one with the blue dots also never goes past the pink line. So in both cases, those sequences are bounded above by M. So both sequences are bounded above by M. Okay, and of course this M is not unique. If we've got M being an upper bound, then we can have this green line above it, M prime, that is also an upper bound. So we've got M, it never goes above that. M prime, it never goes above that. Anything else afterwards, it still doesn't go above that. Okay, so the upper bounds are not unique. All you need to worry about is that your sequence stays below whatever it is. Okay, so this M and M prime are examples of upper bounds. Right, you can have more than one. Okay, so that is if it is bounded above, and we've got a very similar thing for bounded below. We just swap everything around. So a sequence A sub n is bounded below right, we just swap everything. So instead of M being above, we now have something that's below. So bounded below if there is a number let's say little m. So capital M, that's for above, little m, that's for below. Such that. And then we just swap it from what we had before. So m is less than or equal to an for all n. In other words, the sequence is always bigger than the lower bound. So here m is called a lower bound. Right, so bounded above with the upper bound, bounded below with the lower bound. Yeah, we can draw a nice picture of this as well. So let's do this one over here. Okay, maybe it like levels off, something like that. So we can have this pink line here, little m. That is a lower bound because the sequence here with the white dots never goes below the pink line. So we say it's bounded below. We could also have something like this, something similar to what we had before. Right, the blue one could just like oscillate. And again, it never goes below that pink line, so it's bounded below. And like we did before, we can put in another line, m prime. If it doesn't go below the pink line, then it certainly doesn't go below the green line. And anything else below that are also lower bounds. So m and the green one, m prime, are examples of lower bounds. Yeah. And you can have anything else below that that is also a lower bound. Right. Any questions on these two, bounded above or bounded below? They're all good. Okay. Last picture for today. If the sequence is bounded below and bounded above, then we say that it is bounded. Okay, and then we've got a last picture to go with that. So if the sequence an is bounded below and bounded above, then we say it is bounded. Okay, so bounded below plus bounded above, we just say that it is bounded. It's just the words we use for it. Okay, and we can draw a picture of this. So we've got some sequence, whatever it may look like. Okay, but here it must be bounded above. So we need to be able to draw a pink line above the sequence at capital M. It never goes above that. And let's use blue line for below. We can draw a blue line underneath the sequence, maybe over here, for little m. And we see that for all values of n, it doesn't go past those two limits. So it doesn't go above the pink line. It doesn't go below the blue line. So it's bounded. So bounded just means it's between two limits there. So doesn't go above the upper one, does not go below the lower one. Yeah. Any questions for this last part? Yeah, all good. Okay, Thursday we'll go through the monotone convergence theorem with the proof and applications. Those that are a bit rusty with the limits and limit laws, please make sure you go through that. Okay, there will be a lot of limits, limit laws, squeeze theorem, L'Hopital's rule. Okay, all of those limit stuff, that will come on Thursday. Okay, so please tomorrow go through all of that, and tonight, if you are a bit rusty with that. Right, any questions before we go? All good. Okay, so please revise that for Thursday.